Hi guys, going to go through the diagnostic assessment paper. I'll do separate videos for section A and section B. I figured this time you didn't necessarily need to see my face because it's what I'm writing that's more important, so this way you can blow it up to whatever size of screen you've got. Hopefully this should be a bit quicker than the paper I reviewed before the diagnostic assessment week, because of course you've done this one and you've given thought to it. So just to clear a few things up and show you where the little tricks were and things to be aware of. So first question then, so outer subshell electron configuration of element in group 16, and the only trick here I suppose is the fact that they said group 16, and that's using that terminology that has 18 groups in the periodic table and accounts for the D block in the middle. So remember, take 10 away from that, and that's essentially talking about the conventional group 6. So then if we're talking about group 6, then we know that an atom that is an element in group 6 would have atoms with 6 electrons in its outer shell. So we've got to find one of these that's appropriate for that. I think sort of the trick answer is this one here, the P6, because you might think 6 electrons will plug for that one straight away. But just don't forget that in each principal energy level, there is an s orbital as well that takes 2 of the electrons, which only leaves 4 remaining to go into p orbitals, so our answer there was A. The second one, Geiger and Marsden fired alpha particles at a gold foil. What happened in their experiment? So you might remember that this one was the one that gave evidence for the nuclear model of the atom. Remember, the nucleus is a tiny, tiny, tiny space in the middle of an atom, so most of the alpha particles went straight through. Every now and again, a very rare event occurred where an alpha particle was scattered through a very large angle or came back to a decent extent, and that's where it had a direct collision with the nucleus. And from this, Rutherford was able to conclude that most of the mass and positive charge of the atom is concentrated in the centre. So if we just go through these answers, then the alpha particles were scattered randomly, or most went straight through and were sort of undeflected, so not really. And he was able to generate a mathematical description of the atom where the scattering was not random. It was the ones hitting the nucleus that were deflected. Most alpha particles passed through undeflected. I'm happy with that one. Many bounce back. No, it was a very rare event for them to bounce back. No alpha particles were deflected, well, some were, so that one can't be true. So it must be B. 3, you've got to be very careful with which molecule has no lone pairs, because potentially you could have just looked at A and jumped to an incorrect conclusion. Now, A, beryllium chloride, as a molecule, beryllium's in group 2, so it's got 2 electrons in its outer shell. So if you try to draw a dot and cross diagram for this, you'll see that around the central beryllium atom, there are 2 pairs of electrons, and then there are no lone pairs. But it does specifically say which molecule has no lone pairs, so these ones are counting as lone pairs for the purpose of this question. Thus, what we've got to go for is something that's got atoms potentially with restricted numbers of electrons, or electrons that are all used up in bonds, and our answer is going to end up being this one. So this one, BH3, will have boron at its centre. Boron's in group 3, so it must be forming single covalent bonds with hydrogen atoms. And remember, hydrogen's only got 1 electron in its outer shell, and therefore will have no lone pairs. Draw these, there'll be a lone pair on the nitrogen there, and then the fluorines here will have 3 lone pairs on each of those. So your answer to that one was D. The volume in centimetres cubed of 4.4 grams of carbon dioxide at room temperature and pressure. So room temperature and pressure, remember, we know that 1 mole of a gas occupies 24 decimetres cubed. Then check the units that they're giving you in this question. They've said in centimetres cubed. So I would be underlining that as I go through, just to highlight to myself so I don't get the answer wrong, because it could be that they give you the answer for an easy slip up in there, remember. So we're looking at 24,000 centimetres cubed, because remember there's 1,000 centimetres cubed and a decimetre cubed. But that's 1 mole. We've been given a mass of carbon dioxide, so the first thing that we've got to do is work out our number of moles of carbon dioxide. So our moles of carbon dioxide is going to be equal to the mass, 4.4 grams, divided by the molar mass, it's 44 grams per mole. That's one that I suppose I just know from doing thousands of times. But carbon is 12, 2 lots of oxygen at 16 apiece, so 32 add 12 is 44. So that gives you 0.1 mole, multiplied 0.1 by 24,000, and it's 2,400 centimetres cubed, which is B. Okay, 5. Which reaction will give you this as a product? I think the first thing to do in a question like this would be to count the number of carbons and just make sure that we're not adding or taking away any carbons here. So you've got 1, 2, 3, 4, 5, and if you do that, in fact, all of these have 5 carbons, so we can't eliminate any that way. We've then got our first one here, though, which is an aldehyde. You can see that it's an aldehyde because we've got CHO written on the end, and it's not an OH. Remember, if it OH, then it would be an alcohol. But CHO is indicating we've got an aldehyde group on the end there. And we know that we can reduce aldehyde groups back to alcohols, but because they're on the end of a chain, that would become a primary alcohol, and that OH there would be in the wrong position. So it can't be that one. It would leave us with an OH on the end if we reduced this. Then we've got treatment or heating or basically reaction of the double bond with water. So adding water across the double bond. So this is looking far more likely. Both of these conditions, the concentrated sulfuric acid followed by water, and also the steam and phosphoric acid under pressure, would both result in the addition of water across that double bond. So we just got to figure out where we're going to put it. Now, if we look at this molecule here, we've got the OH on the 3rd carbon. So if we look at this, if we were to treat this particular molecule with this and add water across, we could add a hydrogen on there and we could add an OH group there. But if we did that, the OH group would be on the 2nd carbon, not the 3rd, so it can't be that one. Similarly, with this one, we could put an OH there and an H there. They're the same molecule. It's going to give you the same result. This is the only one that allows us to introduce a hydroxyl group onto the 3rd carbon, because what we can do is we could add an H across there and an OH across there, and just leave us with a single bond connecting those two there. So our answer is D. Which statement about the reaction RCl plus NH3 goes to RNH2? Remember, this R group here generally stands for an alkyl group, so you don't need to bother about it. It's just telling you that we've got a chloro group connected to a carbon, and the rest of the molecule doesn't particularly matter. We're just looking at this here. Now, the reaction that would take place here is some sort of substitution reaction. If I were to draw the carbon and the chlorine, and then I'll just put other things coming off. We've got ammonia here with its lone pair, partial negative charge on the nitrogen because it's more electronegative than the hydrogen, partial positive charge on the carbon because it's bonded to the more electronegative chlorine atom. So we will get a nucleophilic substitution reaction with electrons moving like this. So let's have a look at the options that we've got here. So it says an amine is formed. We're looking at this. An NH2 group is a primary amine, so that one's absolutely correct. So that's going to be our answer. We'll just have a look at the other ones and see why the other ones aren't our answers. It says RCl is acting as an acid. Well, they put that one in there to trick you because you may know that ammonia is a base. But in our world of A-level chemistry, when we're talking about acids and bases, usually we're talking about proton donors and acceptors. So an acid is a proton donor. Now, in this case here, this has got nothing to do with the donation of protons. And the protons, synonymous term for hydrogen ions. Got no hydrogen ions moving around there. Sorry. This reaction is electrophilic substitution. Well, it's a substitution reaction, but it's not electrophilic. This involves a nucleophile here attacking this centre. This is nucleophilic substitution. And an amide is formed, well, an amide is a group that you'll meet next year that has this. Well, that's a secondary amide, and you can also have a hydrogen there and have a primary amide, but you haven't covered amides yet, and it's not going to be that on an AS paper. Okay, so we recognise that as being an amine. And number 7, right, the mass spectrum of ethanoic acid has a peak at M over Z 45. Which species has caused this? This is all about fragmentation. So remember, when you put organic molecules into a mass spectrometer, first thing you do is bombard them with electrons in the hope of knocking out an electron from the molecule and creating a positively charged species. That positively charged species can then be accelerated and pass through the mass spectrometer. And in time of flight mass spectrometry, after you've accelerated all of the ions up to a particular kinetic energy, you then let them drift throughout the mass spectrometer. And the amount of time it takes to drift to the detector gives you an indication of how heavy they are. The heavy ones travel more slowly. So the only thing that gets through to the detector is a positively charged species. And the first thing to check in a question like this is whether they've got positive charges. And they've given you positive charges. Now, what does it mean by this m over z is 45? Well, we assume at A-level chemistry that the charge on all of these ions is +1. So we've only knocked one electron out. And indeed, they've only given you singly positively charged ions. So although it says a mass to charge ratio, they've all got a charge of +1. You're dividing the mass by 1. So in effect, this mass to charge ratio is a mass of 1.
Dad,
Hang on, Ems, hang on, let me just pause the video. Sorry for the interruption. I think where we're up to there is just establishing that these were all 1 plus ions, and therefore m over z produces just m. So we're looking for something that has a molecular mass of 45. So you just got to add these up. So the thing with the molecular mass of 45, I think, is B. So we've got 12, 32, and 1. What's formed at the cathode when aqueous aluminium sulfate is electrolyzed? Now, there's different ways of thinking about this at A-level, and you can just learn some rules in terms of reactive metals are never discharged. Hydrogen's discharged in preference. Sulfate ions aren't discharged, you'll get oxygen produced instead. But let's just remind ourselves of what the situation would be here. So if we just draw a little diagram of an electrolytic cell, so my positive electrode and my negative electrode. Okay. Remember, my positive electrode is the anode, my negative is the cathode when I'm carrying out electrolysis. Now this is aqueous aluminium sulfate, and that makes a big difference, remember, when we're carrying out electrolysis in aqueous solution or whether we're doing it with the molten ionic compound. Because if you're carrying out electrolysis with the molten ionic compound, you've got nothing else than the elements that are present in the ionic species. But if you carry out an aqueous solution, the water can get involved as well. So we know in aluminium sulfate, you'll have aluminium ions and you'll have sulfate ions. Sulfate ions will be attracted to the positive electrode. Aluminium ions will be attracted to the negative electrode. But the simplest way to think about this is to say that we know we've got water in here as well, and water, to a very, very tiny extent, auto-ionizes to give you a small concentration of hydrogen ions and hydroxide ions. So you'll also have hydroxide ions competing for that electrode, and you'll have hydrogen ions competing for that electrode. And then we've got to know what wins. We've got to know what's discharged. Now, your rule for A-level is that reactive metals are not discharged. This is because if you think about like a lump of sodium, you put sodium in water, it reacts with the water, gives away its electron, and would prefer to be in that situation a sodium ion. Reactive metals, as far as A-level go, are going to cover group 1, group 2, and aluminium. If you have those, they are not going to be discharged in aqueous solution. What will be discharged instead are hydrogen ions. Hydrogen ions will travel to the cathode, gain electrons, and turn into hydrogen gas. Or you can write the equation with the reduction of water. Okay, either one's acceptable at A-level, but I'll just keep it simple here with this. At the anode, what we're going to get is we've got competition between the sulfate ions and the hydroxide ions, and our rule for A-level is out of all the things that they can give us, halide ions can be discharged at the anode. They've got a strong preference to being discharged. Yet every other ion, negatively charged ion that we're going to meet, doesn't in general get discharged at the anode. So what's going to win here is hydroxide ions. So hydroxide ions are going to be oxidized. They're going to lose electrons and turn into oxygen. You'll have to produce water as well to take away some of these hydrogen ions, and we're going to release electrons. I have got here, I want to, if I put 2 of those there to even those up, 4 of those, and 4 electrons. So that's the reaction that's going to go on there. Now, I've given you all of the background there. We only need to work out what's formed at the cathode. So the cathode was our negative electrode there. So we are going to get hydrogen. Which term correctly describes cyclohexane? So cyclohexane, 6 carbons around in a ring. Don't be tricked. There isn't one of these. And there we haven't got a delocalized ring of electrons. We've not got a benzene ring. So it is not an arene. It's not an alkene because it doesn't have a double bond. And it's not unsaturated because it doesn't have a double bond. It is an aliphatic compound, which means it's a hydrocarbon not containing a benzene ring. Urea, the formula CONH2 in brackets 2, percentage of nitrogen by mass in urea. So the way that we do this is we need to work out the overall relative molecular mass of this species. So we've got a carbon, which is 12, add an oxygen, which is 16, add 2 lots of everything in the brackets, and that's the way I tend to do it rather than do them separately. So nitrogen's 14, hydrogen's 1, 2 of those, so we've got 16 in the brackets, 2 lots of 16, so we've got 36, 40, yeah, 32, 48, 60. And it wants the percentage of nitrogen in there. Well, for 1 unit of that, we've got 2 atoms of nitrogen. So if we want to do percentage by mass of nitrogen urea, we've got 2 lots of 14. That's the relative atomic mass of nitrogen, divided by 60, times by 100, and that's just shy of 50%, so it must be that one there, D. Right, property of solid iodine. Now remember solid, so we need to know a little bit about the appearance of the halogens and how they change going down the group. Remember iodine is a grey solid at room temperature and pressure, but if you watch it for a minute, and especially if you stand it in something that provides it with a little bit of heat, you'll see a purple vapour come off it. So this is one of those interesting elements that sublimes at room temperature and pressure, and faster if you allow it to. If you heat it up, it misses out the liquid state. So let's have a look at the options here. So firstly, it's not purple in colour, that's its vapour. It melts when heated at room temperature. No, it turns directly into a gas. That's a bit of a trick. And then we've got these two here. It's very, very soluble in water, or it dissolves in organic solvents. Now, you should remember from handling these, and you did a practical in elements from the sea, where you use chlorine water, bromine water, iodine water, and then you also probably added some cyclohexane. Now, what you should have seen was by adding cyclohexane, you could draw all of the halogen, or most of the halogen, into the organic layer. This is because the halogens dissolve far better in organic solvents than in water. So it's not very soluble in water, but it does dissolve in organic solvents. Right, this one here, silver nitrate solution is added to solutions of sodium halides. So remember, silver nitrate, we're going to use this as our test for halide ions. Chloride ions give us a white precipitate, bromide give us a cream, and iodide ions give us a yellow. They've also talked about solubility in ammonia, but let's try and knock some of these off first. So chloride would give us a white precipitate, happy with that. Iodide would not give us cream, it would be yellow. Chloride would not give us cream, it would be white. Iodide would give us yellow. So these two potentially could be correct. But then you might remember that you can add ammonia solution to differentiate between these different precipitates, because their colours do look relatively similar. So if you want to be absolutely certain, you add some ammonia solution, and the chloride is soluble in ammonia, whereas the iodide is insoluble. So it's this one here, D. What, if any, is the action of concentrated sulfuric acid on HBr? Right, you might remember that one way of making the hydrogen halides is to treat a solid halide salt, something like sodium halide or potassium halide, with concentrated sulfuric acid. And what you'll end up doing is making the hydrogen halide and say sodium hydrogen sulfate, something like that. This is fine if you're trying to make hydrogen fluoride and hydrogen chloride, but you might remember that with the bromide and the iodide, bromide ions and iodide ions are strong enough reducing agents to go back and react with the sulfuric acid. And if they react with the sulfuric acid, they can reduce it. they can reduce the sulfuric acid either to sulfur dioxide or sulfuric acid. Iodide ions will do one, bromide ions will do the other. And it may be that you can just remember which way round this occurs. But if you get stuck in an exam and you can't quite remember, use oxidation states to help. So in terms of reducing power, iodide ions are stronger reducing agents than bromide ions, in that they want to give away that electron. It's in a larger ion, it's further from the attractive force of the nucleus, and is more easily lost. So looking at the oxidation states, the sulfur changing oxidation state here, it starts here at +6, and sulfur dioxide ends up at +4. In hydrogen sulfide, it ends up as -2. So this one is far more reduced than this one. So in terms of what's going to reduce what to what, bromide ions will reduce sulfuric acid as far as sulfur dioxide, whereas iodide ions, more powerful reducing agent, will take it all the way to hydrogen sulfide. So what's the action of concentrated sulfuric acid on HBr? Well, the HBr with its bromide ions will turn it into sulfur dioxide. It's not no reaction, we should know that, and there's no sulfur that's formed in any of these, so we should know that too. Right, which molecules form permanent dipole bonds as its strongest intermolecular bond? So what we're looking for here then is a molecule that's polar. Okay. Firstly, carbon dioxide, not polar. Remember, although you've got polar bonds, delta plus, delta minus, these two dipoles cancel out. Same thing happens in tetrachloromethane. You've got this regular arrangement of the chlorines around positively charged carbon. So the centre of negative charge is coincident with the centre of positive charge, and there's no overall dipole. So then we've got these two. Now these two contain oxygens bonded to carbon, so you'll have polar bonds, and also they've got asymmetry in the molecule. And both of these then could form permanent dipole bonds. But it does say as its strongest intermolecular bond. So if it's going to be its strongest intermolecular bond, we've got to think of that bond that's one up on the rung. And the one that's one up on the rung are hydrogen bonds. So do we have the ability to form hydrogen bonds in these? Well, in this molecule here, we've got an aldehyde. We don't, because we haven't got the hydrogen directly attached to the oxygen. In order to form a hydrogen bond, you've got to have the hydrogen directly attached to an oxygen, nitrogen, or fluorine. However, in ethanoic acid, we do, because in ethanoic acid, we've got lone pairs on this oxygen and this one. And we've also got our partially positively charged hydrogen directly connected to an oxygen. So we've got the ability to form hydrogen bonds there. So both of these can form permanent dipole interactions, but this one can form that super strong type of permanent dipole interaction known as a hydrogen bond, and classed as something different. So it's this one here, A, that forms permanent dipole bonds as its strongest intermolecular bond. 15. A student says that bioethanol is carbon neutral. Which option provides evidence that disagrees? Again, underlining things we go through, disagrees with the student's statement about bioethanol. So the reason why they're saying it's carbon neutral, remember carbon neutral is basically saying over the life cycle of making and then burning the particular fuel, there's no net emission of carbon dioxide. Now, biofuels are often described as carbon neutral because during their growth, they take in carbon dioxide from the atmosphere in photosynthesis and turn that into the biomass of the plant. Obviously, the crop doesn't look like this, but as my classes know, I can only draw flowers, so that's what we draw. Then we harvest that. There we go. It's dead on the floor. And we turn that into bioethanol. So there's generic sort of tubey, not tube thing, flask, whatever you want. So this is the bioethanol. And then we put the bioethanol in a car. There you go, instantly recognisable. Then in the exhausts that come out, we burn it and the carbon dioxide comes out. And if you look at if you just balance atoms of carbon here, and the same number of carbons that went in come out, and overall the same amount of carbon dioxide that goes in comes out. Okay, lovely. However, they never end up as being carbon neutral because there's other inputs of energy into this process. For instance, in making fertilizers and pesticides and stuff like that for the crops, for the farming machinery, for transport of the fuel, stuff like that. And if that energy comes from other sources that aren't from biofuels or aren't from renewable energy sources, and then the whole process is not, strictly speaking, carbon neutral. So let's have a look then. So we're looking for a statement that provides evidence that disagrees with the student's statement that bioethanol is carbon neutral. So the fact that it gives off carbon dioxide when it burns, well, that was part of our argument for being bioneutral. That's fine. It's just it's the same amount as taken in. So that's not right. It's made from crops that absorb carbon dioxide. Again, that's part of our little diagram there, isn't it? So that's not right. Energy from conventional power stations is used to make it. That's the one. So this energy input here, there will be some from conventional power stations. Valuable land is used up growing the crops used to make bioethanol. That's a disadvantage of biofuels, and especially in countries where there's a conflict between feeding the population and making fuel, but it's not relevant to this question here. Let's see. 16. Which substance cannot be made in a single step from ethene? So if we look at ethene here, remember, as soon as you see something like this, you should be saying, right, I know this is going to be some sort of addition reaction. I know we can add stuff across the double bond. What are we adding in order to make this? Well, looking at the formula, C2H4, we've added one H and one OH. We've added H2O. Can we add H2O across the bond? Yeah. In fact, we've seen that in a previous question, so we can do that. This one here, so C2H5Br, we've added an H and a Br. Looking at the formula, can we add HBr? Yeah, we should know we can add HBr. Remember, you know, the old mechanism, delta plus, delta minus. We've got electrons from the double bond attack that hydrogen. Yeah, fine, lovely. C2H6. So can we add two H's? Yeah, we can get hydrogen to add across the bond. That's the one that you use like the platinum catalyst for or whatever. Then this one, NH3, we've added. Have we ever seen that? No. And in fact, NH3 tends to behave more as a nucleophile, a source of electrons. Well, if we look at the first step in the electrophilic addition mechanism, electrons come from the double bond. So we would end up with two things wanting to give away electrons. Not going to happen. Okay, so our answer there is D. Right, which substance will not give 3-methyl pentane when reduced with hydrogen? If I were you, I would probably draw 3-methyl pentane to start off with. So 1, 2, 3, 4, 5 methyl group on the third position. And then I'd have a look at these and I'd probably start drawing them out if you're not so great at visualizing these in your head. 2-ethyl bute 1-ene, so draw the 4 carbons for bute, double bond in the 1 position, ethyl group on the 2 position. Okay. Can we turn this into this if we reduce it? Well, when we reduce it, what we're doing, just get rid of that little underlining. Oops. Because that's going to get in the way. When we reduce it, what we're doing is we're going to lose that double bond and it will turn back into a single bond. And we'll add a hydrogen here and a hydrogen there. But the beautiful thing about skeletal formulae is you can do that without having to worry about the hydrogens. Let's just draw that again, having reduced that bond. Oh, it's exactly the same as that. Okay, so that will give that 3-methyl pent 2-ene. So pent 2-ene and it's 3-methyl. Well, what I'm going to do is I'm just going to highlight that because that's what we're aiming for. If we reduce this group, so we just take it away, then again, we get back to that. 2-methyl pent 1-ene. This one, we reduce that. Now we see that we would have the branch on the wrong carbon. Okay, you can instantly then, because you're probably starting to recognize the trends, 3-methyl pent 1-ene. Yeah, we'll end up with that methyl group on the third carbon that we want. But this one, we don't. Right, which is not a reaction 2-methyl propan 2-ol. Now this is the one that you do in Elements from the Sea, or alternatively, if you teach us one in What's in a Medicine, where you synthesize a chloroalkane from an alcohol, and you use 2-methyl-propan-2-ol. So this may have seemed familiar to you, maybe not, doesn't really matter. But 2-methyl-propan-2-ol, so if we draw propan-2-ol, and then we stick a methyl group on the second carbon, we're looking at this thing here. Okay, so firstly, reaction of an acid anhydride to form an ester. Remember, an acid anhydride is a carboxylic acid derivative. Now, you can react carboxylic acids with alcohols to form esters. An acid anhydride is just like a more reactive carboxylic acid, so that would work. Oxidation to form a ketone. Well, we know we can oxidize alcohols, but can we oxidize this type of alcohol here, where the carbon is attached to 3 other carbons? We've got a tertiary alcohol. We certainly cannot oxidize this one, so that's not going to be possible. So the answer is going to be B, but we'll just check the others. Dehydration to an alkene. Now, dehydration, we've seen that in this section as well. We're going to take away an OH, and we're going to take away, say, an H from this one. Lovely, we can do that. Reaction with HCl to form a haloalkane. That's the experiment I just told you about. So reacting with HCl, because what will happen is in the first step of the mechanism, HCl, remember, is a strong acid. So if you do it with aqueous HCl, you'll have H plus ions kicking around. So in the first step, the oxygen, off the screen here. In the first step, the oxygen is protonated, which makes it into a better leaving group. The carbon here, partial positive charge. You've got a chloride ion with its lone pair of electrons. Chloride ion can attack that carbon there. That bond breaks. And kicks out water. Okay. So that reaction can happen. And then the last two in this section, which statement about instantaneous dipole-induced dipole bonds is correct? They become weaker with increasing chain length of an organic compound. Well, no, remember, as you increase the chain length, you increase the opportunity for ID-ID bonds to form along the length of the molecule, and their overall strength will increase. So that's not true. They become stronger with increased branching in organic compounds. Well, remember, when you branch an organic compound, rather than allowing chains like this to lie close to each other and interact quite strongly, branches sort of get in the way of them packing together, increase the distance between them or reduce the number of points of contact, so it reduces the strength of the ID-ID. So that one's clearly wrong. They occur between molecules rather than atoms in molecules. So what that's saying there is, if we just look at a portion of a molecule, they're saying they occur between molecules, as we've drawn here, not between particular atoms in molecules. There isn't an interaction there or between there and there. We know there's a covalent bond. So this is the one. So this one. I'm getting confused myself. So that one is correct because they occur between molecules rather than atoms in molecules. And then the last one, this one annoyed me because on your syllabus they want you to pretty much always state that dipole-dipole bonds are stronger than instantaneous dipole-induced dipole bonds. And if you are one of my students, will know that I make a big point out of, well, it depends which molecule you're looking at. And sometimes the component of the intermolecular bonding that's provided by instantaneous dipole-induced dipole bonds is greater than that provided by dipole-dipole bonds. Just look at the trends and the boiling points of the hydrogen halides. However, here they want you to appreciate that sometimes instantaneous dipole-induced dipole bonds can be stronger than dipole-dipole bonds acting between molecules. So yeah, there we go. Silly syllabus. But anyway, so in any molecule, they're not always the weakest intermolecular bonds. So that is C. And then the last one, which of the following is a redox reaction? So in a redox reaction, the way that we're going to tell this, because we've not got little half equations with electrons moving, so we've got no giveaways there, you're going to look at the oxidation stage of the species involved. If if elements change oxidation states, then you know that it's a redox reaction. So you just go through this and you start assigning oxidation states or oxidation numbers to these. So sodium, oxidation number is 0 because it's in its elemental form. Hydrogen +1, oxygen -2. Straight away, sodium's become +1 there. -2, +1, 0. Right, okay. So the hydrogen has been reduced because it's gone down in oxidation state, whereas the sodium has been oxidized, it's gone up in oxidation state. And you can check the others and see that nothing changes in these. Remember, in a redox reaction, you'll always have one species that's being oxidized and one that's being reduced. So which of the following is a redox reaction? A. Right, much quicker than the other paper. I will go through section B in the next video.